This crystal, made by Mother Nature many thousands of years ago, polished by man, is one of the largest specimens of quartz that you are ever likely to encounter. This man-made chip, merely a fraction of a millimeter wide and nestled neatly in the eye of a needle, is one of the smallest and most powerful laser crystals now in commercial use, but by no means the smallest crystal. In this bottle, made by my predecessor, Michael Faraday, one morning in 1856, there are countless millions of crystals of gold. You need an electron microscope to see them, and before very long we'll show you what they look like. Now, crystals and lasers possess a beauty and a sparkle that sets them apart from most other scientific things. They're also of enormous practical and scientific importance, so much so that Professor Phillips and I feel that we can introduce you both to the major developments and to much of the excitement in modern science by considering them during the course of these Christmas lectures. We shall range freely right through the alphabet of experimental science, from archaeology through to zoology. Let me begin by acquainting you with some interesting properties that crystals possess. Ever since the days of the ancients, man has been aroused by beautiful, sparkling, symmetrical, durable, and rare crystals. And here are some of them. Amethyst, nice flat face. Beryl, pyrite, beautiful crystals. Those have been in existence for millions of years. This one was made in Strathclyde University 4 years ago. It was grown like that. If I took that cap off, it would evaporate. That's why I keep it there. This crystal, made in the Chinese Academy, is a very powerful laser crystal with neodymium in it. Now, what is a crystal and what isn't a crystal is a very difficult question to answer. Let me tell you, this decorative object, it's called a cut crystal. It's not a crystal at all. It's glass. This facsimile of the largest diamond ever discovered, the Cullinan diamond, 3,000 carats. It was cut into 4 stars of Africa. One of them is now in the imperial crown. The diamond itself, of course, was a crystal, but this facsimile is not. It's a glass. This strange-looking object, called a kidney ore, it's iron oxide, hematite. That's a crystal. This glass bowl, made in Pennsylvania a few years ago, it's a ruby. It's a man-made ruby, and it's a crystal. You'll hear much about rubies because the first laser ever, as Professor Phillips will tell you, was made from a ruby. This is 99.99% aluminum oxide. There's a trace of chromium, which makes all the difference. This rather uninteresting looking solid, a lump of green rock, but when you polish it, it really looks spectacular. That's malachite, rich in copper. Sometimes you can tell whether a solid is a crystal by using what the geologist, mineralogist, and chemist calls the property of cleavage. Now, when crystals are this plentiful, like this one of rock salt, sodium chloride, and it grows that size in Poland, you can quickly tell whether it is a crystal because it breaks very easily, and you can put them together again. Cleavage, nice, easy parting. Now, obviously, you're not going to determine whether a diamond is a diamond by taking a hammer at it. That would be a very profligate thing to do. One doesn't proceed that way. Now, sometimes, as you may have seen in museums, if you go to the Natural History Museum, for example, you'll find that crystals look different under artificial light. That's fluorite. Look at it under ultraviolet light. And look at this one under ultraviolet light. This is the origin of the term fluorescence, by the way, because fluorite, the mineral, tends to exhibit this property. Look at this little spectacular example here. That's a crystal made in Dorset recently of cesium iodide. But my favorite mineral crystal, so far as fluorescence goes, is this rather uninteresting, nondescript solid. Look at it. Under UV light, it sparkles. That's a beautiful green fluorescence of the mineral known as willemite. All the early television sets had a screen made of willemite. And many of the items of equipment used by Rutherford and many other scientists in the early years of this century had willemite as a coating. In fact, Bryson and I have an experiment here which we're going to show you. Let me tell you what we have. It's an evacuated tube, like a television set of early vintage. At this end, we have a metal electrode. The other end is charged, and that's where the willemite coating appears. Bryson is going to apply an electric field. We are going to have these tiny particles of negative charge, the electrons, traveling right across. There you see that beautiful luminescence. Now, in that evacuated space, we have a Maltese cross. We're now going to introduce the Maltese cross for a reason which will become obvious in a moment. We're now going to test whether it is true that when electrons travel from one point to the other in an electric field, they do so under, in straight lines. And if you apply the voltage, there you are. You see a beautiful Maltese cross. Thank you, Bryson. Well, now I want to draw to your attention some interesting properties relating to the shape and growth of crystals. Here's a material known as alum. Here it is in powdered form. You can buy it in any chemist's shop. It's very cheap. And you can dissolve it up in water until you can dissolve no more. That's to say, you produce a saturated solution. If you fish out from there the largest crystal that you can lay your hands on, tie a piece of cotton around it, and then let it dip like that, and wait 3 days, or thereabouts, leave it undisturbed, put it in a cupboard. You will grow a crystal. Well, we started growing them. This is my colleague, Dr. Peter Maddox's attempts in the last few days. If you're very, very patient, you can grow them that nice, or this nice. Bryson is going to put that in a cupboard. And on the 6th day of this Christmas lectures, we're going to see what they're going to look like. In the meantime, let me tell you a little bit more about these 6-cornered but 8-faced objects. It's called an octahedron, 2 pyramids, base to base. Sometimes alum grows like this. Sometimes it grows as a cube, like that. And rock salt, sodium chloride, the stuff that you put on your fish and chips, sometimes that grows like that, and sometimes it grows like this. Is that really true? Does that really occur? It's a sort of schizophrenic state, if you like, that this salt, they're like human beings. They're not quite sure which way to go. Now, we're going to illustrate that shortly, but not before I introduce you to this magnificent piece of equipment that we have to my left, and also Paul Overton, who is going to run it for us. This is a scanning electron microscope. It's a very powerful instrument. What it does is fire electrons at any object, the shape of which we wish to examine in great magnification. The electrons come back from the surface, and then we form an image. Now, Paul has been very smart to put in a pound coin. The Queen's head is to be seen there, magnified 10 times. I'd like you to show our friends, Paul, the power of this instrument. Move up progressively on the scale of magnification. You might wish to go to the rim of the coin, first of all. That's a 1985 one, as you can all see. Right, now, we're up already to times 70, to times 80, to times 150, to times 400, to times 850. I can't keep abreast of him. Now, by the time we get to 2,000 or so, it's so greatly enlarged, we could be looking at a lunar landscape. Now, what we want to look at, having introduced you to the schizophrenia of salt, is just ordinary common salt. Now, for that purpose, I would like a volunteer. Why don't you come down, the lady in the red jumper? What's your name?
I'm Jocelyn.
Jocelyn. Very pleased to meet you, Jocelyn. Now, I want you to have some training with Paul here. I want you to produce some of the best possible pictures of sodium chloride, high magnification. You go ahead. We should be able to see in a few moments, if everything works well, and these two manage to get the sodium chloride into a nice visible condition. That seems to be coming on quite nicely. Now, what shapes do you see there, Jocelyn?
I see cubes and octahedrons.
That's fine. That's splendid. Look, let me just remind the audience here. She's seen a cube and she's seen an octahedron. So they coexist. Now, sometimes you get what we call truncated cubes or truncated octahedra. The edges, the corners rather, have been cut off. We're going to come back to those in a short while because we're going to try and explain why it is that sodium chloride has this interesting property. Thank you, Jocelyn. It's very kind of you. Now, with Bryson's help, I'm going to try and see if we can grow some crystals live for you in this lecture. I'm going to take, first of all, this mica. Many of you have seen mica. It's got very good insulating properties. One of its great advantages is that you can cleave it very nicely if you have a steady hand. And my hand, for some strange reason, isn't terribly steady at the moment. We cleave a piece like that so as to get a nice cleaved face. Now, whether that's good enough for you, Bryson, I'm not certain. You put the ammonium iodide on that surface, and let's see if we can generate some lovely crystals. While Bryson is doing that, I want to show you a movie clip of another material which is trinitrotoluene, TNT. That's a very high explosive. If you melt it gently and then let it grow on an optical microscope, here it is. This is what you would get. Beautiful growth moving inexorably across the microscope slide. That's what TNT would look like if you just control the conditions appropriately. Now you can grow crystals from solution, from the melt, as many of these have been grown, or from the vapor. In fact, to grow a crystal from the vapor is a very important thing to do these days, and I want to explain to you why, and I want to explain to you with the aid of this delicious object which Pippin has just produced. I want another volunteer. Are you very hungry? Are you very hungry? Come along. What's your name? Nikki, right, Nikki. I don't want you to take too much of this. I'm going to give you a knife. I want you to be very, very careful. I want you to cut a piece. Cut it along there. Very, very carefully. That's it. Good. Right the way you go. And I'll cut another piece along here. Good. And now you take that piece out. You can keep that, incidentally. There you are. Put it on your hand. Good. Take it. Very good. Sorry we didn't give you a serviette. You sit down and eat that quietly. All right? Thank you, Mr. The whole purpose of showing you that was just to remind you that a cake like this, like many other cakes, have layers in them. And that's the whole point about why the modern electronics industry, in developing some of the most powerful and advanced new lasers that they want for putting into the compact discs of the 21st century, they're using a technique in which they take a crystal. Now, there's a crystal which you're going to hear a great deal about in this course of Christmas lectures, the gallium arsenide crystal. It's a spectacularly specular crystal. There it is. Now, what we do, we have a working model here. I'm going to show you how this working model illustrates the principles that people like the electronics industries use for generating layered crystals. They put the crystal of gallium arsenide initially on this rotating table. They have a source inside a very high vacuum. They have a source of gallium and of arsenic and of aluminium. And they program the computer in such a way that you always have the gallium coming in, you always have the arsenic coming in, but only intermittently do you have the aluminium. See, there's no aluminium coming in when this little shutter is in that position. It's only arsenic and gallium. So we're laying down gallium arsenide at that point. Now we're laying down gallium aluminium arsenide. It's like chocolate and cream, and so forth. Now, on this projector, we have the beautiful result. You may think this is just a sheet of paper with lines on it. On the contrary, each one of these lines is 1,000,000 times as thin as a sheet of paper, as the thickness of a sheet of paper. And the spacing says gallium arsenide, gallium aluminium arsenide, gallium arsenide. That's what gives rise to some of the most powerful lasers that we've got. Now, how are we doing on these crystals? Can I take a look? Oh, that's splendid. I wonder if we can have that up on the projector here. That's very nice. Those are the crystals of ammonium iodide. Now, this, you see, this again is schizophrenia. That's a square-shaped one, and that's rather a triangular-shaped one. Thank you, Britain. Now, I want to go back to the question of the shape of crystals. I told you about this octahedron and that cube. It's very easy for us to understand why that happens. If I take a model, a series of solid objects, this is the first one. That's an octahedron. Let's say that's a crystal which is in a nutrient solution, and it's growing very steadily. Suddenly, I say that it can't grow at the corners, at the vertices. If that happens, then we're going to have a crystal that's going to look like this. There we are. We've called that a truncated octahedron. If we continue that process, we're going to end up on the next stage like that. And I think you can see what's coming. It's pretty obvious. Here is our truncated cube. And lo and behold, in the fullness of time, we have our ordinary cube. And that's it. Now I want to show you that dynamically. That's a static illustration. It's quite true. But there's something rather pleasurable using a computer modeling system. And some friends at the University of London have done a very nice job. And I want to show you this on the next film clip. Here's a crystal, an octahedron growing. Suddenly, there's going to be no further growth at the corners. Just wait for it now. Now it's going to continue to grow, but these faces are going to become less and less like hexagons, and they're going to become triangular. And this has become square. And then ultimately, we're going to get through to the point where it becomes a cube. So that's it. It's a very, very nice cube. Now, before I leave this subject of shape and morphology, I want to tell you an interesting story which concerns this Stone Age axe. This is called obsidian. It's very much like, chemically, like quartz. This material here, or that obelisk behind me. It's predominantly silicon dioxide. It's thrown out of volcanoes. Primitive man has used it from time immemorial. It's very, very sharp, and it's been used by, say, the North American Indians to hunt the beasts of the wild. Recently, the curator of the Vancouver Museum has realized that if there's any residue of blood on that axe, and that if that axe has been buried for millennia, you can scrape the blood away, put it under an optical microscope, and look at the shape of the hemoglobin crystals. That's the molecule of the blood. And from the shape of the hemoglobin crystals, you can tell which animal had been hunted, whether it was the moose or the caribou or the bison. How can you do that? It's because there were two clever American scientists in Philadelphia in 1909 who published this book. We have it in our library. It's an atlas, a compendium, which gives you a description of the shape of the hemoglobin crystals of all known mammals, fish, and birds in 1909. Here it is. Here's what they look like for the marsupials. And here, incidentally, are some of the photographs that they took of the hemoglobin crystals. Now I want to turn to interesting properties of crystals. Some crystals are very, very sensitive to light. You've all used a color film, I'm sure. On this color film, there are literally millions upon millions of crystals. If I took every crystal from here and put them side by side, stretched them out, they would go from London to Birmingham. In fact, if you look under an optical microscope at those crystals, they would appear something like this. There they are. Now, that's not the natural color. They look like that, just in the way that oil looks like that when you have it on the surface of water. It's the thickness effect that gives you that color. Now, with Paul's help and another volunteer, could I have another volunteer? How about you, next to the lady in red? Come down. I want you to look at silver bromide crystals. What's your name? Dylan Thomas? Fine, come and sit down. Good. Now, would you show Dylan and Paul how to use this instrument to the best of advantage to see that we can get silver bromide on our screen? Silver bromide crystals have this interesting property of being converted into silver when light shines on them. Now, we're up at times 22. We want to go really very much higher than that. Very much higher indeed. What do they look like in 3 dimensions? Now, we're at times 900. And we're gradually coming through, and we're seeing some rather nice-looking crystals, which I can point out to you here. Yes, very nice, very good. Fine. These are the minute crystals of silver bromide. Well done, Dylan. Thank you very much for your help. Very good. Now, when light falls upon silver bromide, it is converted to silver. I want to show you a series of slides. The first slide is of an engine and an engine driver. What I'm going to do is progressively call for increasing magnification. The next slide now, slightly larger magnification. The next one, here we are, getting a larger and larger picture of this gentleman. The next one, please. You see his rosette, yet again. Now, we've reached a magnification at this point of 2,000. 2,000. This is one large hexagonally, vaguely hexagonal shape of silver. Now, if Nicky were magnified 2,000 times, he would be 2 miles high. That's the magnification there. But that's as nothing compared with what you can do with modern electron microscopes. The one that I used to use in Cambridge is capable of 10 million magnification. And on the next slide, here we are, if we can dim the lights, you are now looking at individual atoms of silver. I can point to you this silver atom with 6 other atoms surrounding it. This is an enormous magnification, 10 million times. Nicky would stretch from London to Tokyo if he were magnified 10 million times. There was a great American poet, Ralph Waldo Emerson, about 100 years ago, long before atoms were really proven to exist. He wrote a couplet which said, "Atom from atom yawns as far as moon from earth, as star from star." That's a tremendous insight, a poetic insight into the way in which nature is built up. Well, now, those are light-sensitive crystals. I want to talk next about pressure-sensitive crystals. But before I do so, could I ask, how many of you use quartz watches? Let's have a show of hands. Well, I would say about half of you do. Here's a lump of quartz. Now, the reason why I want to talk about quartz for a moment and about this solid is because there was a gentleman and his wife, and you're going to see their photograph in a moment. Here they are. Does anyone recognize this lady? Perhaps her husband is standing next to her there. Anyone recognize that lady? What did you say? Madame Curie, the only lady ever to win the Nobel Prize twice. Her husband and Madame Curie came to the Royal Institution on many occasions. Pierre Curie stood here and described a discovery that he made way back in 1890, the discovery of piezoelectricity. That's a big word. All that that means is that if you take a crystal of quartz and press it, you develop an electric field across the other faces. With this gadget here that Bryson has put together, and our friends in Northampton have given us this titanium lead oxide crystal, watch what happens. No doubt about it, it can pick up the pressure that I apply. You put the other trick together, Bryson, while I show our friends something which is very familiar to you. Look, the gas lighter of today, can you see it? I'm not sure if you can see that clearly. You can see that electric discharge coming there. There we are. Well, that's converting muscle power to electrical power via piezoelectricity. Now, Bryson, just let us set this oscillating. You see what he's done there now? You can see that in unison, we're getting that oscillation to occur, just as that spring goes up and down. Now, that's the principle of a quartz watch, but in reverse. If I show you this Japanese finger that I have here, resting on it, there is a small quartz tuning fork. And what happens in a quartz crystal is that you simply apply periodically pulses of voltage, and that causes the tuning fork to do that in unison. So you can control the time with very, very high precision. That's exactly the principle of the quartz watch. Now, there are many other things that I could tell you about crystals, which are very interesting, but I think it's appropriate for you to listen now to the Deputy Director, Professor David Phillips, who is now going to tell you about the properties of light. Professor Phillips.
So what is light? Well, it has dual nature, and we need to have both descriptions in order to understand it. I'd like somebody to try and help me show just one of those descriptions. Can I have a volunteer? Perhaps this lady here. Now, all I want you to do is to go with Pippin to that rather odd-looking lamp that you see up there, and then I'll describe why it is that you can see me. You can see me because from that lamp is coming a stream of small particles which are bouncing off me, entering your eyes, and that causes something which you can see. It's something like this. Well, let me assure you that those photons, as they're called, carried no mass, but they certainly carried some energy. How much energy? Well, that was a white light source. And a white light source has photons of all different colors. I have a bowl full here. I'm going to tell you that blue photons carry more energy than red photons. Now, I need to be able to explain that. Let's begin by using a crystal or a prism to create the colors of the rainbow that we're familiar with in just the way that Isaac Newton would have done. I need to pull the screen down to see this. And with any luck, in just a minute, we'll have a spectrum that we can look at. You see these colors, of course, as the colors of the rainbow. You know what they are. Here we have now a rather nice spectrum, which we should be able to see when the lights are down. The colors which extend from the violet end of the spectrum through blue, green, yellow, orange, and into the red. And I actually have to learn that because I'm colorblind. Now, blue photons have more energy than red photons. Why should that be? I can explain why it should be on the basis of a really rather nice model which is coming along now, and I'd like somebody to help me demonstrate this. How about the girl in front? Please. What's your name? Elizabeth. Well, now, Elizabeth, I have a little job for you. This is a wave model, and you're going to have to stretch right up to be able to do this. I want you to make a wave traveling in space, because the other description of light is that it is a wave. Now, I'm going to help you just waggle that up and down. There we go. And you've made a wave. Now, if we stop, let's just see what happens. You see it reflects from the other end and now comes back. So the other end is just like a mirror. Now, let's do that with ultraviolet light, because I think we get a much better effect. We'll do it again. Why don't you do it yourself this time? And there we go. If we have the lights down, we might be able to see Elizabeth make a beautiful traveling wave in space. There we go. All right, that's fine. Stay there now because I need you a little bit more. I need to do an experiment, so I need one more volunteer. Have you helped? I'm sorry, I'm choosing all the girls here, so I'll try and redress the balance later. Now we need a clock. Now, simple experiment. I want you, Elizabeth, to start the clock by doing that, and when it comes to 10 seconds, just shout stop. And as soon as we start, and you start when I say start, I want you, and your name is? Margaret. Margaret's going to count how many peaks of a wave go past. Just keep counting. Right, so shall we say ready, steady, go? Have we got there yet?
Stop.
5. All right, 5 in 10 seconds. Now let's damp this down again, and let's do it again. But now we're going to make a slightly different wave. Are we ready? You'll have to count quickly this time. Ready, steady, go.
Stop.
13. Many more. Now, if we divide by the 10 seconds, we get the number of peaks which is going past a microscopic stationary observer in 1 second. And that's called the frequency. The frequency in the first case, how many did we count? 5. So it was 5 divided by 10 is half a hertz, it's called. And you counted the second time 15, 13. So it's 1.3 the second time. The second time was a higher frequency, as it's called. And did you notice I had to move the model much more vigorously the second time? That's because, and I thank you both very much now, you can now go back to your seats. That is because the relationship is just that the energy is given by a constant times the frequency. If we go back to our visible spectrum now, that means that the red part of the spectrum, the red end of the spectrum, is of low frequency, low energy, and the blue end is of high frequency, higher energy. But the visible spectrum is really just only a small fraction of possible waves, and we can see it in position if we look up at the large scale spectrum above. At the very lowest energy, we can see that we have radio waves. There is a wavelength of about 1 kilometer. There are radio waves used for communication. Higher energy, we come to microwaves that you would have in your kitchen, for example, and then the infrared, which is just heat. Then we're back to the visible, and now on the other side, which is the high energy end, ultraviolet light, then into X-rays, and now gamma rays, and the energy carried per particle here is so high that it has a drastic effect on the nuclei of molecules and atoms. We will be particularly interested in regions of the spectrum which are just to one side of the visible part of the spectrum. But let's think about colors that we see. Why do we see colors? Well now, very obvious, isn't it, that this bright red sweater is red because these are white light sources. All colors of light are coming onto this surface, but all of the colors except red are being absorbed by a dye in the material. So the blue, the yellow, the green is all being taken away, just the red being transmitted. If all of the color is absorbed, you see black, right? What would happen, though, if none of the color was absorbed? What would you then see? Well, you'd see nothing at all, would you? None of the visible light from this white light source is being absorbed by this solution, which disappointingly is just water. Let me put it there, though, and show that something is not coming through there, because this white light source produces a lot of heat also. And the heat is actually being absorbed by the water, so nothing happens to this detector that I have here. I can replace the water with this solution, which absorbs everything. It absorbs all the visible light, that's all gone. But the infrared gets through. And if I put my detector back in place, with any luck, you should see that although there's no visible light there, my detector will respond, I hope, to the infrared radiation. Not responding very quickly. Yes, it is. Now, our eyes are sensitive to the visible part of the spectrum that we saw because the source of light that we use, the sun, produces mainly that light. We've adapted biologically to use that. But there are some creatures which have learned to use radiation which is invisible to us. Infrared radiation, for example. Here's an example. Here is a snake, a rattlesnake, which has infrared detectors which it can use to catch its prey. There are other examples. And here is Mr. David Smith from RSRE with another one. And I'll let him tell you about it.
Fortunately for me, the rattlesnake is not the only snake having infrared sensors. I'd like to introduce you to Sid, who is an Indian python, a distant cousin of the rattlesnake. And if we can come a bit closer to the monitor, you can perhaps see the infrared sensors around his nose. These are the comma-shaped pits there. And with those, he senses the thermal radiation.
He's a most beautiful creature, but what does he actually see?
Well, we think we can show you what we think he can see with the aid of an infrared camera, which my colleague Martin Thomas is operating at the top of the stairs. If you look at the monitors now, you will see a rather blurred picture. Now, Sid has only a few infrared sensors. If he had many thousands of sensors, he might see a picture more like this, very much sharper.
That's truly amazing, and we're going to learn a lot more about this in a later lecture. But for the time being, thank you very much, David.
Thank you.
When light is absorbed by atoms and molecules, some really quite surprising things can happen. For example, chemistry. To make a chemical reaction go, you usually have to provide some energy, and that's often done in the form of heat. So I'm going to ask Bryson to make a chemical reaction work by providing heat in the form of a match, and the result, I think, may surprise you. And you can see I always let him do that experiment. But I've told you that light carries energy also, and so we can achieve a rather similar effect if we use light instead of heat. And just to be fair, I'll do this one. There we go. Now all I have to do is irradiate that, and with any luck we should get a similar result. There we go. When energy is taken into an atom or molecule, it can be released, obviously, in the form of a chemical reaction, but there are other options open. And one is that the light can be given out of the system again, but the light given out would be of a different color, and we would call that a fluorescence. Now, we have a volunteer, I think, who's going to help me, and I have to say that this is my daughter. It's her main chance to appear on television, so please come down, Sarah. And she's got some fluorescent materials on, I hope, which will give you an idea of what this emission can look like. So if you stand there now, and the lights go down, I think we ought to be able to see that she's wearing a cycling tunic, which would be clearly visible, well, certainly at a disco it would, and certainly is visible on the road. Now, while we're here, why don't we do something else? Here are a variety of objects which you might find which fluoresce quite nicely. And here's something, a bottle of something which fluoresces quite strongly too. Perhaps you can see that that has a rather pretty blue fluorescence. And perhaps surprisingly, I'm going to drink it. Well, Sarah and I are going to drink this. I'll pour it out, and you can see it very nicely. Because of these lectures, we don't see each other very often, so we perhaps will greet each other and drink. Now, can we see the lights going right down? Your good health. I think we'll let you leave that, Sarah. Thank you very much indeed. Go back. Now, did you notice that while we were drinking the tonic, that our teeth fluoresced? No? Perhaps I can show you that again. If I grin hideously at the camera, you might see when the lights go down. I'm really doing that deliberately because false teeth generally don't fluoresce. I'm just showing you that I still have my teeth. The luminescence that you just saw is of a particular type, and it is extinguished immediately when the light source goes off. If I show you that there, it's fluorescing. As soon as the light source goes out, it goes out. Actually, it doesn't. It lasts for about 1/1000th of a second. And we'll look into that later. But there's another kind of luminescence which lasts longer. Some of these minerals we saw earlier fluoresce or phosphoresce. Here's a phosphorescent sample. But in order to demonstrate what I mean by phosphorescence, we brought a character along. And who recognizes who that character is? Somebody there. The Cheshire Cat, yes. Now what happened to the Cheshire Cat?
His mouth
He faded away, but his grin remained, didn't it? Let's see if we can do that. Here's the Cheshire Cat. Now, when the lights go right down, you'll see him fluorescing rather nicely. Can we all see him? And if I put the light out, what remains? But the grin remains, okay? Now, the material that the grin is made of is called a phosphide. It has a long-lived emission, and we're going to be looking at that in one of the later lectures because it's very important. What happens when you excite an individual atom or molecule? Well, in order to describe that, I really need to use the simplest possible device, which represents a hydrogen atom, the simplest possible material. Hydrogen atom consists of a positively charged nucleus, and around which in space there is one negative species, the electron, and it would look something like that. There you go. There's a mammoth-sized hydrogen atom. When this atom gets excited, it produces that effect. That's all that happened. The electron moves from one place to another place. And that corresponds to absorption of light. And what we've shown here is that when light is absorbed, the electron goes from one place to another place, and the reverse process is emission. When light is given out, the electron goes from that place to that place, and light is given out. So we now know how to create light. To create light, you have to make an excited electronic state of an atom or a molecule. Very simple. How can you do that? Well, you can do it by heating things to be very hot, but that's not something we're going to explore in any detail. Another simple way of doing it is to pass an electrical discharge through a gas. And we've got a beautiful example here of such a discharge, and I'd like somebody to help me do this. Someone there, I think, might do nicely. I need somebody else in just a minute. Can you come and stand here? And your name is? Sarah, another Sarah. Let me switch this on. Now, isn't that beautiful? That's just an electrical discharge passing through a gas. Now, what I'd like you to do is put your hand on the back, and she can steer it, you see. Take your hand off and put it back on again. Do it several times. Play with it. It's a toy. Now, that's an electrical discharge. I can show you that, and I can also show you that human beings can conduct electricity if I have another volunteer. But I really ought to have, in the interests of fairness, I ought to have a boy this time. Can I see any boys? Where are we? There's a boy. Can you get out? Is that difficult? Actually, the boy on the end over there, you would do, please. Now then, all I want you to do is take hold. You're going to become friends. You take hold with your other hand, that, and can you go around to the other side, please? And what's your name?
Dominic.
Dominic. Dominic, you take that in your right hand. Sorry, left. I don't know my right from left, do I? And can you go and stand over there so you can see? That's it. Now then, all Sarah has to do is to put her hand on the globe, and we'll see what happens. Did it? It did. Take your hand off. It goes out. Put your hand back on again. It comes up. Now, Dominic, you move your hand along a bit. Yes, and can you see that it's only the bit of the tube that he's holding that is lighting up? So that electricity is going through Sarah along the tube, lighting up that tube, which means it's a very efficient way of creating light and then going to Earth through you. So thank you both very much indeed. That's an electrical discharge. Now, please don't go home and get hold of one of these tubes and do anything silly with mains electricity, because that would be very dangerous and very silly. There are many biological systems which know how to make light, and they do it by a chemical reaction. And we have here an example of some fish which have learned how to make some chemistry work to produce flashes of light. They're called the flashlight fish, and if you look on the screen, you'll see there they are. They have flashes of light on their heads, and that's very useful to the fish in many ways. But the creature which has learned how to do that best of all is perhaps the firefly, and I thought we'd show you a firefly on a very large scale. Now I'm going to make this chemical reaction occur to produce light, and I have one chemical in his tail already. The firefly doesn't understand the chemistry, but he knows very well why he's making the light, because he finds his mate that way. This is what happens. If I add the second chemical, you should be able to see what happens to the firefly. And if I shake that around, you see that's really rather good. We're now attracting glass fireflies all over Mayfair, I should think. But that really is a very beautiful form of light, and we're going to look at all of these again because of their importance to us when we come to the one form of light which I think is beyond comparison. Something I haven't mentioned yet, that is laser light, the light fantastic. Now, you saw in the opening sequence of these lectures the use of lasers in this theatre to make some rather beautiful effects, and we're now able to see that again. In lectures 4, 5, and 6, I'm going to be telling you what makes laser light so special and how we can use it. But now is the time to go back to the world of crystals and find out how light interacts with crystals. John?
Thank you, David. There are just two things that I want to mention to you again. First of all, the question goes back to what Professor Phillips mentioned. Light is absorbed by certain materials, certainly absorbed by crystals. Now, this is a fact that is made use of by gemologists. There are many people in this world who are preoccupied with gems because they're very expensive things. I have here two rubies. One is a real ruby and one is an imitation ruby. Now, the British Museum of Natural History all through the year gets inquiries from various people who say, now, have I got a real ruby here or is it not? Now, the gemologist, the curator of gems in the British Museum, Dr. Roger Harding, he's here today. We've asked him to come along. And in fact, he'll be entering the door in a moment. Dr. Harding, there we are. Thank you, Roger. Roger, tell us which of these, I think I've told my friends already, which of these is the real ruby? You show us how you go about that.
Well, I use a small handheld spectroscope, and I place the stone on the left between the strong source of light and the spectroscope and examine the stone in the light. And I reckon that this one is a piece of glass. Do the same with the second stone. Get the light coming through the stone, and that looks like a ruby to me.
How did you know that? Come and tell me with the aid of this spectrum here. How did you know that?
Well, the spectra of ruby and red glass are quite different. The red glass has a transmission band in the red with no absorption from the yellow down to the blue. But the ruby has distinctive absorption lines in the red at about this position, and in the yellow, a thick, wide band in the yellow at about this position. And it's the pattern that is characteristic of ruby.
It's the chromium in the ruby that gives rise to that.
It does, yes.
Thank you very much. Thank you, Roger. Well, Dr. Harding had, in fact, kindly provided us with an example of what you could see in that little spectroscope. On this screen in a moment, you will see what is observed when you look at a real ruby. Here it is on the top. And when you see an imitation ruby, that's what you see. Now, there's one final thing that I want to do. It's an experiment with Bryson. We have a laser beam here, a helium neon laser beam, which is reflected back. Bryson is going to insert a little object, and I want you to observe on the screens what happens to that initial red spot. The single spot, I hope, is going to be converted into something rather different. We should get, there we are, 6 spots of red light. More about that in the next lecture. Thank you very much.